In this video, we're going to talk about the slow divergence of the harmonic series, and then we're going to look at hopefully a clarifying question on Taylor series. So the harmonic series, remember, is this sum n going from 1 to infinity of 1 over n, and we can see it's related to this natural log function. It's the integral from 1 to infinity of 1 over x is that natural log function. And we've talked about before in class that a logarithm is a very slow growing function, that if you're going to draw that to scale, you would go up 2 feet on the y-axis and right just past Alpha Centauri on the x. So we'll see that kind of reinforced with this harmonic series. So the question we're going to be asked, and I think you'll see in your homework, is approximately how many terms are required to form a partial sum greater than 20? So what we're going to do is to try to tie this to our integral. So if we look at y equals 1 over x, then you can see this drawn here. And if we look at a Riemann sum, if we make these rectangles have a width of 1 and a height that's on that curve, then the area of these rectangles exactly correspond to the terms in the harmonic series. So hopefully that makes sense, that when you plug in 1 for n in the series, you get 1. When you plug in 1 for the function 1 over x, you're going to get a height of 1 times a base of 1 makes this area be 1, which is the first term in our series. When we plug in 2 into the function 1 over x, we're going to get 1/2 for a height, and since the base is 1, that's going to make this area be 1/2, which is exactly the same as the second term in the harmonic series, and so on. So this Riemann sum, this right Riemann sum, represents then that area between the curve and the x-axis. Now, if we look over here in the green statement here, so let S sub n be that nth partial sum, then you can see that we need to make the rectangle go from 1 to n, the integral rather, go from 1 to n, otherwise we're going to have the whole issue of integrating over that vertical asymptote. So what we do is, that means we have to add in the area of this first term separately. That's the 1 right there. Now from this point on, our left Riemann sum, or our right Riemann sum rather, you can see is going to be an underestimate because we're missing these gaps between the rectangles and the curve. So our nth partial sum, where we actually added up all n of those rectangles, those n rectangles, will be less than 1 plus the area under the curve, which would include these gaps that we're not getting there. But we can then use that, since we know the integral of 1 over x is the natural log, and if we're going from 1 to n, that natural log of n minus the natural log of 1, since the natural log of 1 is 0, would just be the natural log of n. So we can use this as an approximation then to our nth partial sum. And we know it's a bit of an overestimate, but that's okay. We're just trying to get an approximation. So if we want to know how many terms, that is n, so what is the n? How many terms are we going to need for that partial sum to be equal to 20? Then we know that we actually need more than whatever we would need to make this, that is, to make that 1 plus natural log n equal to that. So if we say S sub n is approximately 1 plus natural log n, and we want that to be 20, then we can say the natural log of what will be about 19. And so that would be then, n would be e to the 19. And that would be, remember, an underestimate, so we would actually need more than that. But e to the 19th is approximately 178,482,301. So that's a rough estimate, but we probably might need even more than that because of our undercount. Okay? That's just an idea of how slowly that diverges. Okay, because remember what we're saying is that this sum is going to go to infinity. It's unbounded, and yet it's going to take, 178 million of these just to get to be 20. But yet there's no limit to how big it'll get. Kind of crazy. Here is I think, a challenging but maybe clarifying question about how these Taylor series work. So only one of the following can be done with an easy substitution. So we're going to read through these, and you might want to pause the video to think about it a little bit and see if you can figure out which ones work and why the ones that don't work do work. So only one of these would be an easy substitution. So part A is a Taylor series for sine x centered at pi over 4. Part B is a Taylor series for sine of x minus pi over 4 centered at pi over 4. And part C, a Maclaurin series for sine of x minus pi over 4. So remember, we know that our Maclaurin series for sine of x is, it's going to be the odd powers. So it's going to be x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, and so on. So the question is, can we use this to build on any of these here? Now, for part A, that is not the one, that we can't just use our Taylor series and try to translate it over pi over 4, because all of the coefficients here, because it's a Maclaurin series, because we have powers of x, these are all derivatives taken at 0. To be centered at pi over 4, we would need for all of the derivatives to be at pi over 4. They would have to be taken at pi over 4. So I'm going to write that down. All derivatives would have to be at x equals pi over 4. So we would be doing the sine of pi over 4, and then we'd take the derivative at pi over 4 times x, and then we'd have to take the derivative at the second derivative at pi over 4 times x minus pi over 4 squared over 2 factorial, and so on. But because all the derivatives would be taken at pi over 4, we could not use that Maclaurin series whose derivatives are all taken at 0. Now, part B actually would work, because in this case, what we would be doing is taking all of our derivatives and evaluating them at pi over 4, which means we would be taking, for example, the sine of pi over 4 minus pi over 4 is the sine of 0, and the derivative would be evaluated at pi over 4 minus pi over 4 would be 0. So we would get all of those nice derivatives that were evaluated at 0. And in part C, this won't work again, because what we mean by a Maclaurin series is that all the derivatives had to be taken at x equals 0. And when you plug in x equals 0 here, you're going to evaluate at negative pi over 4. And so there again, your first term would be f of negative pi over 4, and your next one would be the derivative evaluated at negative pi over 4, and so on, which are not going to be nice and not going to be the same as these. Okay, very good. So maybe clarifying, going back to this one, this series would be, the function evaluated at pi over 4 would be 0. And then the next one, we know we would be able to, the first one there, we would take the derivative and evaluate that at negative pi over 4. So the cosine at negative pi over 4 would be a square root of 2 over, at pi over 4 would be 0. At pi over 4, cosine of pi over 4 minus pi over 4 is cosine of 0, which is 1. So you would get an x minus pi over 4. So it would be that translation of our Maclaurin series. And then we would get, the next one would be negative x minus pi over 4 cubed over 3 factorial. So I guess we could call that a minus. And so then we would get a plus x minus pi over 4 to the 5th over 5 factorial, and so on. Okay.